Welcome to the Energy Utilities module of the Control Systems Fundamentals for Industrial Networking course. The goal of this course is to enable learners to assimilate the information presented in further training courses, such as managing industrial networks with Cisco networking technologies. This module will introduce you to why the energy utilities industry is moving to a converged network and look at design considerations for an energy utilities network environment. In this module, we will recognize an energy space topology and its components, explain the high-level elements required in the energy space, describe the set of modern energy utility standards, explain main protocols for automated substation, describe key IT utility requirements. Energy utilities such as electricity production systems can be defined as large-scale industrial systems. In this lesson, we will present the high-level components that allow system-wide communications, device control, and security features within a modernized electrical grid. How does electricity get from the power station to us, whether we are in a residential neighborhood, commercial office, or manufacturing plant? Electricity travels tens or even hundreds of kilometers through a network called the electricity grid, which consists of power generation stations, terminal substations, distribution stations and substations, and meters. The power generation station generates high voltage electricity that can be transmitted over very long distances. As electricity flows through the grid, it reaches a transmission station, where voltage is stepped down using transformers. Distribution substations reduce the voltage further in order to supply power to homes and businesses. Distribution substations consist of a primary and secondary substations, which can be found underground, above ground, or suspended from a utility pole. European grids have secondary substations. Electricity reaches the end of the electricity grid when it enters the customer's meter. Most often, the meter is owned by the utility company as considered to be part of the grid. An electric utility or electric power company owns and operates equipment within the electricity grid and sells the electricity to the general public. Available electricity is very important because lack of energy can cause economic loss associated with reduced industrial production. Electric utilities can be divided into three main categories: municipal utilities, rural electric cooperative utilities, and investor-owned utilities. Each utility is responsible for a specific territory where it serves different types of consumers, such as residential, commercial, or industrial. Transmission lines connect utilities to each other so they can exchange energy. This allows one utility to assist another high-demanding utility, preventing a blackout. Within an electric utility, the three top concerns are aging infrastructure, power reliability, and service regulation. The electrical power grid has grown over the years from standalone distribution systems that spanned a limited geographic area to complex and regional transmission and distribution systems that interconnect large geographic areas. In the past, power plants were built close to the end customer to supply the needs of electricity. As they grew, electric utilities joined together, creating a broader utility grid. Combined operations benefited from sharing load coverage during peak times and protecting power with more backup sources. Since the electrical grid evolved through consolidating utilities, the distribution of power is highly inefficient and cannot support anticipated demand loads without significant upgrades to the infrastructure. Climate change-related regulations and a need to increase operational efficiencies has caused utility operators to consider overhauling the electrical grid systems to a smarter system. Such a grid would digitally gather, distribute, and act on improving the efficiency, reliability, and sustainability of electricity services. The next evolution in the power grid is starting with large-scale smart metering deployments. For the next phase of modernizing the electrical grid, utility operators are focused on developing an integrated communications infrastructure. However, there are concerns about transforming the grid to incorporate legacy networks, disparate tools, and tight security requirements. Many utilities still rely on complex proprietary networks where information between operational areas is siloed. These utility operators do not have the tools needed to see, gather information, and make decisions that would result in better operational efficiency. In order to move past these challenges, a common multi-service network infrastructure needs to be developed for the entire organization. A multi-service network would support the utility's current capabilities while allowing for future network expansion to accommodate new applications and services. The goal of the Cisco Connected Grid is to reduce truck rolls, smooth peak power use by allowing customers to use energy in off-peak times. The Cisco Connected Grid consists of several principal components with specific qualities to facilitate these goals, such as data center, a secure and efficient operations center environment which contains the applications associated with data collection, analysis, and control. These data centers can be fully virtualized operations to enable scalability, efficiency, and cost-effectiveness, as well as manageability and security. The operations center. As the central point for analysis of operational data in the smart grid, optimal IP network designs are critical for reliability and performance. Applications residing in the control centers perform a variety of functions, ranging from grid monitoring and control to generation scheduling and market operations. Getting the right data from smart grid intelligent devices to the appropriate applications quickly and accurately and providing a response in real time is the function of the operations center. Field area network. This part of the network is the communication overlay between devices in the utilities network. The FAN requires a communications infrastructure that has the ability to accommodate the needs of diverse applications, ranging from fault location, isolation and restoration, or FLIR, grid optimization, and demand response to the management of distributed energy sources. These services help design an architecture that is scalable and able to meet the needs of distribution automation and distribution energy resources, or DER, use cases in the future, address high availability requirements for security and FLIR use cases, and build security transparency into the fabric of the distribution network. Customer premise network. This design requires for this part of the network address the communications needed within utilities' consumer, commercial, and industrial environments, and determines how the utilities' business requirements can be effectively achieved in a secure manner. Cisco architecture and design services can provide the flexible frameworks necessary to address multiple premises network scenarios and integrate them into a single high-level communications architecture. Transmission and substation network. Cisco services for this network create designs for differentiated levels of service for the various types of traffic traversing substations. They are secure and compliant with regulations governing these networks. The objective is to reduce operation costs for the utilities, provide greater visibility, and increase reliability in these environments. And lastly, utility and regional networks. Cisco design services for the wide area network connect all the network places together in a secure and fully differentiated manner, mapped to the requirements of the various applications flowing across it. This service helps improve the manageability of the network. The Field Area Network, or FAN, is the communication network overlay for the electric distribution grid. The Cisco FAN strategy is to create a multi-service, secure, smart, reliable, and scalable communication network that enables a diverse set of use cases, such as advanced metering infrastructure, or AMI, distribution automation, asset management, workforce automation, public electric vehicles charging stations, public lighting, and distributed generation and storage. Implementing a unified FAN architecture provides utilities with the following benefits. It deploys a single converged IP-based architecture, enabling utilities to make communication technology decisions based on application and deployment requirements. Reduces operational costs by streamlining network operations based on IT best practices and eliminates the need for proprietary architectures. Enables quick and cost-effective turn-up of future applications based on integrated multi-service capabilities. There are three distinct components of a utility. One major smart grid consideration is how connections are made at the substation. The topology of a legacy substation shows how evolving utilities networks consist of devices and nodes that are interconnected in a network. The legacy substation topology correlates with the advanced substation topology, which contains two parts, a station bus and a process bus. A key component in the structure of this topology is an Ethernet communication switch. The type of topology depends on network application and company preferences. For example, a star topology may be used for a station bus. A separate ring topology may be used in station and process buses, etc. When comparing the legacy of the advanced substation, several facts should be noted. In the legacy substations, devices communicate through a combination of rigid wiring and low-speed serial communications. Intelligent electronic devices within the system transmit data through wires connected by output and input ports. The system is flexible, impractical, and limited in its scope of control. In many cases, communications between intelligent electronic devices are not feasible. In the advanced substation, the IEEE 61850 communication is achieved through two application domains: a station bus, an application domain that attaches relays and remote terminal units to the LAN, or a process bus, devices that communicate current and voltage measurements through the LAN. Note that standard IEEE 61850 will be discussed later in this module. The network topology of the substation is divided into two areas: the station and process bus and the multi-service bus. The process bus facilitates switch yard device connectivity to intelligent electronic devices, while the station bus facilitates interfacing to the intelligent electronic devices. The IEDs within the station and process bus are the substation devices that control switchyard equipment, such as circuit breakers, cap banks, and transformers. Intelligent electronic devices sense data from the switchyard power equipment and send commands to grid infrastructure such as circuit breakers, voltage regulators, and transformers. IEDs typically contain multiple protection, control, monitoring, and communication functions. Recent models support IEEE 61850 for substation automation. The IEDs facilitate communication between the process bus devices and the station bus. The process bus conveys unprocessed power system information like voltage and current samples from switchyard source devices to the IEDs. The data received is processed into measurements and translated into control and protection decisions. The station bus interconnects IEDs, distributed controllers, and human-machine interfaces and provides the connection to the WAN router. In order to realize the same cost-efficient, high-speed benefits used in computer networking industries, Ethernet was adopted as the main communications technology for advanced utility networks. Ethernet is a simple Layer 2 protocol that uses well-known popular tools and devices, such as routers and switches that are currently present within utility business networks. Ethernet LANs can encompass multiple physical topologies, for instance redundant trees, stars or extended stars, rings or dual rings, and so on. Usually logical topologies are built on top of the physical topologies. For example, VLANs can be used to provide logical separation between IED devices. In the majority of modern Ethernet LAN deployments, a redundant tree topology is used. Such design could be used to connect process bus networks inside a substation. In this type of design, every access layer switch has a redundant path to both aggregation layer switches in this network. This topology has Ethernet loops, which have to be broken according to IEEE 80D.1d. The ring topology is simple from a physical perspective, but it does not provide clean traffic separation. All VLANs must be configured on all switches in the topology, which leads to poor segmentation, isolation, and security. The most important characteristics of the ring topology are inefficient bandwidth usage, non-deterministic latency that depends on the position of particular pairs of intelligent electronic devices. Traffic between IED4 and IED2 shares the same bandwidth with traffic generated by another IED on the path between switch B and switch F. This situation can change if the blocked port moves to another point in the network. In the ring topology, Ethernet network loops are managed by spanning tree protocol or rapid spanning tree protocols. These provide maximum recovery time from 50 to 60 seconds depending on how STP or RSTP is used. To reduce recovery time, deploy the resilient Ethernet protocol when implementing Ethernet rings in substation networks. REP typically converges the network in less than 100 milliseconds. To prevent traffic loops while providing load balancing capabilities, the redundant tree topology has the proper links blocked for a specific VLAN. This approach allows for traffic separation between the intelligent electronic devices. This could be accomplished by pruning VLANs that do not need to transmit to the attached IEDs. For example, IED1 and IED3 are part of the red group, where access switches C and D have pruned access to the green VLAN. IEDs attached to access switches D and F do not have access to red VLAN. The redundant tree provides better scalability and bandwidth usage than a ring topology. By assigning the root bridge role for different VLANs evenly on both A and B switches, traffic is load shared. This topology also improves resilience and security by means of the smaller broadcast and multicast flooding domains, and provides better quality of service because the jitter is lower due to traffic separation. Supervisory control and data acquisition, or SCADA systems, gather real-time data from the electrical grid, ensuring system reliability. Functioning as a supervisory solution, SCADA monitors the grid from a remote location. SCADA file recorded events to a specified location while monitoring process conditions. If a potential hazard is detected, like an imminent outage, an alarm is sounded. SCADA subsystems connected to the network provide an additional level of control. Subsystem components might include controllers, such as programmable logic controllers, that are programmed to control a series of steps within an automated process, or programmable automation controllers, which are more robust controlling applications. Human-machine interfaces, which are graphic-based user interfaces that instruct PLC and PAC controllers. IEDs, which collect data and report directly to SCADA. Remote terminal units, which monitor systems and report data to the SCADA. RTUs also receive instructions from the SCADA to control devices within the system. And lastly, communication networks, which connect the supervisory system to remote terminal units. Physical security devices restrict access to system components and detect and identify threats to the system. Equipment used by the SCADA system must be protected from physical damage, unauthorized access, or destruction. Access to any equipment by visitors and personnel must be controlled and monitored. There are several physical security options available to utility environments, from the basic fence protection to automated video surveillance systems. When developing a security solution, utility owners should consider the following: restricting access to facilities with gates or fencing, utilizing access badges, restricted key systems, or security tokens to limit access authorized personnel. Deploy identity measures such as photo IDs and visitor passes to manage access to company property. Monitor entry to critical areas and facility perimeters using alarm systems. Record and store video surveillance, and post signage to warn off potential intruders. The physical security devices rely on an IP network infrastructure to route video streams and alarm events to monitoring centers and recording devices for logging purposes. There are various important substation physical security components, such as the following: badge readers. Badge readers deployed at every access point are able to identify and grant access to authorized personnel. The access gateways communicate with the physical access manager at the operations center, and the authorization request is granted via the LDAP Active Directory server. Video surveillance. The goal of the IP cameras is to protect the perimeter gate of the substation and access doors to the control house. The IP cameras support power over Ethernet and wireless connectivity. Video streams are recorded locally at the substation at a ruggedized media server. The operations manager at the operations center is able to manage cameras and media services located at a large number of substations. Video streams from a viewing client and the cameras always go through the media server, which acts as a proxy. In order to successfully migrate a legacy communications system to an Ethernet solution, utilities will need to implement an MPLS IP core network. This transitional network joins a variety of technologies that make an IP network available while continuing to support existing TDM and legacy applications. MPLS IP networks are cost-effective, efficient, and reliable. In addition, MPLS IP networks allow new devices and applications to be deployed. MPLS IP networks are ideal for supporting operational processes and communications requirements when migrating to a modernized electrical grid. Due to the large geographical area that electrical grids cover, one challenge with introducing an Ethernet-based communication system are the gaps within the networks. Based on how large the gap is, there are several wireless solutions that help support an enterprise-wide networks. These solutions would include a WPAN, or IEEE 802.15.4G, a wireless personal area network, which enables a one-to-one radio frequency communication between devices that are close in proximity, such as Bluetooth devices. In a utility grid, industrial routers such as Cisco IR500 enable a WPAN solution. WLAN, IEEE 802.11, a wireless local area network enables communication between two or more devices. This network is also known as Wi-Fi. A WLAN is ideal for transmitting Ethernet data packets within a small localized area. WMAN, IEEE 802.16, a wireless metropolitan area network such as broadband enables many devices to communicate over long distances. Worldwide Interoperability for Microwave Access, or WiMAX, is a secure wireless network that transmits data at high speeds. The infrastructure is often provided by cellular service providers, making this a cost-effective solution. Cisco Connected Grid modules provide utilities the option for a private-owned wireless network. WWAN 3G, a wireless wide area network, enables many devices to communicate over very long distances. This network uses 3G technology and utilizes satellite communication. In this lesson, we will present energy utility standards and how they are changing within legacy plants due to new government regulations around grid security. Government regulations around grid security are driving utilities to implement new operating procedures. North American Electric Reliability Corporation, for example, was commissioned by the Department of Energy to implement critical infrastructure protection standards, for which utilities must comply. Utilities must demonstrate that they have created electronic security perimeter zones around critical cyber assets located in transmission facilities. These requirements are driving utilities to implement new communications procedures to ensure compliance and avoid hefty fines for non-compliance. The current NERC CIP standards regulate security measures for bulk electric systems, including power generation and transmission facilities. IEC 61850 is a relatively new international standard for communications and systems within the substation. IEC 61850 is unique in that it is not an old serial link protocol recast onto TCP/IP Ethernet. IEC 61850 was originally designed to operate over modern networks and delivers new functionality that is not available from legacy substation protocols. IEC 61850 standard defines the requirement for substation automation. IEC 61850 has been divided into 10 parts. The most important aspects of communication within IEC 61850 are covered in the following sections. IEC 61850-3 provides the general requirement for the substation automation equipment. IEC 61850-5 provides the communication requirement for the devices. IEC 61850-7 defines Goose and GSSE that are substation event message services. And lastly, IEC 61850-8 and -9 provide the specific communication service mapping over Ethernet. The core components of the IEC 61850 standard are as follows. An object model describing available data from various primary equipment and from the automated substation functions. To accomplish this goal, the functions of a substation are divided into subfunctions called logical nodes. LNs are the core element of this data model. A specification of the communications between the IEDs and the substation automation system. The standard leverages generic substation events, GSEs, for providing a fast and reliable method to transfer event data over the substation network. GSE is further subdivided into generic object-oriented substation events, or GOOS, and generic substation state events, GSSE. A configuration language that exchanges configuration information between the tools used for substation engineering. To address this requirement, the standard specifies the Substation Configuration Language, or SCL, which creates a hierarchy of XML-based files that describe devices and their capabilities. Another important standard for electrical substations is IEEE 1613. This standard lists key requirements for networking equipment to withstand the harsh ambient temperature and humidity conditions, electrical ranges, dielectric withstand, electrostatic discharge, and electromagnetic interference immunity requirements in power substation. IEEE 1613 explains two classes of influence immunity. Class 1 is for communications devices used for general-purpose substation communications, where temporary loss of communications or communication errors can be tolerated during the occurrence of surge withstand capability, electrostatic discharge or radio frequency transients. Class 2 is for communication devices used for substation communications, where it is desired to have error-free, uninterrupted communications during the occurrence of such transients. To transmit time-critical operating data messages, network devices should meet Class 2 capability requirements. KEMA, or KEMA, a worldwide energy consultancy organization, provides management and technology counseling services to form and calculate the energy value chain that incorporates business and technical advising, operational support, inspection, testing, and certification services. KEMA offers testing and certification classes including type test certificates, ensuring equipment is compliant by administering a series of tests against a set of recognized standards. Product certificates are awarded to products that operate according to international standards. Reports of performance document tests administered according to instructions provided by the customer. Tests performed may be based on a recognized standard or specific requirements. These reports provide test results. This does not indicate the product passed the test successfully. And lastly, inspection reports. These record tests monitored by DNV-GL inspectors at the customer's location. DNV KEMA developed a series of IEC 61850 test tools, which are widely used by network operators and utilities. Device managers also use these tools to check that products conform to IEC 61850 standards during the development phase. DNV KEMA offers the following IEC 61850 test tools: an IEC 61850 protocol analyzer, a client simulator, a Goose simulator, an SCL checker, and an SCL multi-IED simulator. In this lesson, we will present device protocols used for consistent and reliable communications between devices as legacy grids become more modernized. Power grids all over the world implement serial interface protocols such as RS-232, 485, X.21, and V.35. These interfaces are considered legacy protocols in IP networks and are not prevalent anymore. A lot of our routers still support some of these interfaces, however. In the next few slides, we will review some of these protocols and discuss how energy utilities are resolving this challenge. Transitioning from legacy protocols and older standards has become increasingly more common. The new trend in adaptable communication protocols is the IEC 61850 standard, which supports interoperability within a multi-vendor environment. The structure of the IEC 61850 is highly advanced and object-oriented. Modbus, a well-known legacy protocol, was designed for very low bandwidth rates that can run on EIA 232, 422, and 485. Modbus works as a master-slave protocol, where the master initiates all communication. The protocol allows up to 247 slaves per master. The Modbus protocol provides a framework with message structure, synchronization, functional codes, and exception response. The function codes are very specific to the functionality being performed, such as reading coil, reading discrete inputs, writing digital inputs, and so on. Another well-known industrial protocol is Distributed Network Protocol version 3, or DNP3, which is optimized for use in SCADA communication. It is one of the most widely used and supported protocols by SCADA vendors. The goal of DNP3 is to reliably transmit small packets of data with the messages arriving in a strict order. The message can include any amount of application data, even 0, if the command is transmitted. Originally, the physical layer of DNP3 transmitting could be implemented by means of RS-232 if short-distance point-to-point communications were required, RS-422, which represents a bidirectional extension of RS-232 for industrial networks, RS-485 if multi-point communications were needed. Modern industrial networks have changed so organizations can operate over longer distances and wider geographic areas, which is why DNP3 was adjusted to use TCP/IP for the transport on network layers and the Ethernet protocol for the physical layers.
The Modbus protocol is still in use in the automation world because it can connect IP Ethernet networks. Comparing the Modbus stack illustrated on the left versus the updated Mod stack on the right, the main change in the modern network is that Modbus now uses TCP/IP as a transmitting protocol. Another change is that instead of having one master and multiple slaves, it has clients and servers. For example, HMIs or PLCs would be clients, while input-output racks would be considered servers. Significantly, Modbus is no longer limited to one master with a number of slaves. Instead, any number of clients can access any number of servers. A Modbus TCP/IP application data unit consists of the traditional Modbus protocol data unit, which is also present in the Modbus over serial line method, and a new Modbus application protocol header, shortly MBAP. The function code and data definitions of Modbus protocol data unit remain intact. TCP/IP uses registered port 502 to send Modbus application data units through the TCP/IP network. Modbus will continue to be popular for its simplicity and the fact that there are many users with Modbus knowledge in the field. DNP3 transmits data using serial and IP communications. The DNP3 over TCP/IP and UDP/IP specification was introduced by the DNP Technical Committee in 2000 and defines the process of serial DNP3 encapsulation into TCP/IP packets. DNP3 is a good fit for the data acquisition space because it transports data as generic values, has a robust set of functions, and was designed for wide area communications network. Standard IEC 61850 uses an object-oriented approach, a key benefit of the open standard over legacy protocols. According to this approach, control protection, monitor and metering capabilities, as well as physical components, are divided into 92 small virtual units called logical nodes. Multiple logical nodes communicate with each other to provide specific functions such as voltage control or generic automatic functions. As you can see from the illustration here, there are lines of communication between the components at each of the levels. For example, an XCBR at the process level function exchanges voltage readings to the CSWI in the bay level set of functions. This in turn sends specific messages to the HMI at the substation level. This object-oriented approach hides the complexity of the level functions from components at different levels, such as the XCBR functions at the process level and HMI at the substation level. Despite a number of advantages over Modbus, IEC 60875-5 and DNP3, IEC 61850 has additional implementation overhead. It is significantly more advanced than its legacy counterparts, which is why implementation has been slow to take off. IEC 61850 determines many services for the data objects of the logical nodes. These services not only include regular commands of control, reading and writing, but they also offer a new and wide range of services for grouping data objects, reporting and logging, as well as sending fast messages such as Goose and GSSE. The Goose protocol, specified in IEC 61850, is intended for distributing event data throughout the whole substation network. Goose messages send top priority status information such as trip commands or interlocking information, which is transmitted suddenly and then cyclically at enhancing intervals. Goose uses a multicast exchange. Substation automation equipment interacts using low-level Goose multicast messages without disruption. Better priority of Goose packets over other communications guarantees that these messages are transmitted without garbling. To fully meet the case, substation devices must support beneficial QoS traffic shaping features, which allow specifying different priority levels for various packet types. Redundancy provides the feature of transparent resiliency. In modern power substations, redundancy is a paramount necessity for Ethernet communication because downtime causes serious consequences, even in the event of a switch or cable failure. The IEEE 61850 standard uses two main redundancy protocols selected for substation automation, which are described in the document IEEE 62439-3. These include Parallel Redundancy Protocol, or PRP, and High Availability Seamless Redundancy, or HSR. Substation automation systems need to ensure continued services and have to incorporate fault-tolerant solutions. That is why the Network Communication Redundancy Protocol represents one of the paramount parts of a substation automation system. To survive network failures, various standard redundancy protocols can be used depending on topology and convergence time requirements. For example, Rapid Spanning Tree Protocol, Media Redundancy Protocol, and Parallel Redundancy Protocol, and others. As you can see by the examples listed in the illustration, some of the recover times are so tight that protocols such as Spanning Tree and REP are not sufficient. There are additional redundancy protocols under the IEEE 62439 that can be used to meet these requirements, such as PRP and HSR protocols. Parallel Redundancy Protocol, or PRP, does not change the actual topology like other protocols do. It runs using two separate networks. Each frame is duplicated on the side of sending nodes and transmissions through both networks. The destination node processes the first frame it receives and discards any duplicated frames. The PRP layer provides replicate and discard capabilities while hiding the two networks from the upper layers. This approach eliminates downtime associated with network failure and topology reconfiguration or procedure switchovers. PRP redundancy functions are implemented by end nodes rather than network devices. This is a key difference from other redundancy protocols like RSTP or MRP. Each end node is attached to two similar but separate LANs that operate in parallel. The LANs must be isolated so that one LAN is not impacted by the failure of the other. Redundant LANs must not be powered by the same source. Both networks are completely identical in terms of MAC level protocol, but they may differ in performance metrics, transmission delays, and topology. Various applications have different requirements. For this reason, PRP specifies several types of end nodes. The dual attached nodes, or DAN, critical nodes that connect to both networks. Single attached nodes, SAN, and critical nodes that connect to only one of the networks. Single attached nodes that need to communicate with each other should be connected to the same LAN. Virtual dual attached nodes, or VDAN. Single attached nodes connected to both networks use a redundancy box, or red box. This solution allows SANs to connect to both LANs for high availability. The red box operates like a proxy on the part of its virtual dual attached nodes. High availability seamless redundancy, or HSR, further develops the ideas of PRP. Both protocols are defined in the IEEE 62439-3 standard. HSR, in contrast to PRP, is designed for use in ring topologies. Both protocols use two network ports, but the HSR's double attach node, or DAN-H, connects the two interfaces forming a ring. Since there is no second interface, it is not possible to connect single attached nodes directly into an HSR topology without breaking the ring. However, single attached nodes can connect to HSR network using red boxes as a VDAN. From the switchover time perspective, HSR operates the same way as PRP. It sends duplicate frames to both the ports of an HSR network. In the case of a failure in one area of the network, transmissions are sent by other parts of the ring. This approach provides zero switchover time and does not necessitate two parallel networks. On the other hand, an HSR topology requires a ring form, so it is less flexible from an installation perspective as compared to PRP. Another drawback of duplicate transmission is that only 50% of the network bandwidth is effectively used for data traffic. Substation precise timing synchronization is required to ensure measuring devices that are connected to the utility grid have accurate clocks. The clock's accuracy is measured based on a national standard and can range from millisecond to microsecond, depending on the application. The following are examples of measuring devices that require precise timing synchronization. Fault recorders record power faults and disturbances. They generate a timestamp when an important event occurs. Events are recorded at the substation and are transmitted to a central location for analyses. Accuracy to within 1 millisecond is typically required for this. Sequence of event recorders produce a chronological list of state changes within a monitored device. State changes are time-stamped and transmitted to a central source for real-time or post-disturbance analysis. To compare which event occurred before the other, timestamps of 1 millisecond accuracy are required. Phasor measuring units continuously measure voltage and current, as well as frequency of transmission lines. Measurements are time-stamped and sent to a centrally located PAA for further analysis. It is also important to synchronize timestamps from all substations and provide measuring accuracy of within 1 microsecond to perform accurate phasor analysis. Accurate clocks enable sophisticated analysis of real-time and post-disturbance faults and events within a short amount of time. This leads to faster and more reliable fault isolation and resolution, and better planning of transmission resources on the electric grid. In this lesson, we will look at key IT considerations for the energy utilities network. The key IT requirements in the energy utilities network environment include the following: security principles, security management, automation, data analytics, network management, billing contact center, and metering. Substation network security is one of the most critical requirements that can impact substation operation reliability and availability. Key security principles include providing access control, data confidentiality and data privacy, threat detection and mitigation, as well as device and platform integrity. The purpose of access control is to ensure that network access is limited to only authorized personnel and only valid devices are part of the grid network. It can be achieved by using role-based access control with authentication, authorization, and accounting, or AAA, for users and authenticating every device and application connected to the grid, such as routers, switches, servers, workstations, and IEDs. The goal of using network segmentation, secure connectivity, and encryption is to ensure data privacy and integrity for customer and utility data. The purpose of threat detection and mitigation is to protect critical assets against cyber attacks and insider threats. Access lists, firewalls, and intrusion prevention systems, as well as device logs, are used to provide threat detection and mitigation. Another important security principle is to provide device and platform integrity to ensure that devices and meters cannot be compromised easily and are resistant to cyber attacks. These security services should be deployed at each networking protocol layer wherever it is applicable. Complete substation network security should include the deployment of security solutions at OSI layers 2, 3, and 4. Substation security management addresses security requirements from 3 perspectives: security service provisioning, network security monitoring, and regulation standard compliance. For each of these security management areas, substation network availability and attack resilience are the primary objectives. Additional network data protection requirements include data integrity and data confidentiality. Security Event Management, SEM, is a component of substation security which processes security-related event data in real time for threat management, malicious activity, and incident response. The sources of event data include firewalls, intrusion prevention and detection systems, networking devices, security software, logs of host activity, and so on. Security Information Management, or SIM, is the critical part of substation network management, which is responsible for log data analysis, for compliance reporting, user privileges, and resource access. The sources of log data are from monitoring the host system, security logs, directories, and access management systems, transaction logs, and various application logs. There are 4 combined characteristics that make a modern electrical grid smart. The Industrial Automated Control System, IACS, must be observable. System operators must be capable of being fully aware of the grid state at all times. This is achieved through the use of sensor data and control commands. Controllable. The system must be able to adjust to a change in variables in order to drive the grid to any desired state. Automated. Rapid changes need to be programmable and automatic, changing conditions without human intervention. Integrated. The system must be intelligent and efficient by utilizing the network's ability to connect systems and processes. Of these characteristics, one key step in modernizing a utility grid is to implement substation automation and convergence. Substation automation enables advanced protection and control functions while offering the ability to monitor the grid's performance and health. Convergence of the network enables increased reach for the substation data for the purpose of remote access and control. Deploying a secure communications infrastructure allows utilities to control and automate the grid. Condition-based and proactive maintenance programs can take advantage of an automated system's improved visibility and thereby avoiding unplanned outages by detecting stress and enabling preventative maintenance. Until recently, data was simple for utilities. The most data-intensive parts of utility networks were related to the customer, like billing. During the process of generation, transmission and distribution of electricity, the traditional electrical utility only collects data about customer consumption levels. Smart power grids have changed this approach. To improve the amount and quality of data that modern utilities have for analytics, advanced metering infrastructure and intelligent supervisory control and data acquisition systems should be deployed. Today, utilities are faced with large amounts of information. Data management strategies need to be upgraded to handle and analyze this information quickly and effectively. Data from meters, substations, transformers, and other elements on the distribution and transmission system helps distributors to monitor and manage various things in their characteristics, such as device asset life. To cope with such a large amount of data, power utilities can use big data applications. The network is the foundation of a smart grid for utilities. That is why network management frameworks should be considered. Network management allows utilities to assess the grid, make management decisions based on the information available, and apply the necessary control. Network management should tie into energy management in the smart grid, offering configuration management and secure live updates for uninterrupted operations. Network management should control a multi-service network and security infrastructure, such as distribution automation and advanced metering infrastructure, substation automation, and distributed intelligence. Network management also allows utilities to manage a network comprised of legacy devices and more advanced smart devices together in one system. A robust network management system can provide fault management for the substation network through the use of protocols such as SNMP and syslog by monitoring and correlating events. Configuration management can be provided through the implementation of SSH and access to the device CLI, as well as administrative access controls via Radius and TCS/CSS systems. Security can be enabled with protocols such as Cisco NetFlow to provide flow-based packet accounting and so forth. In the electric utility market today, electricity is no longer a product, but customer service. That is why one emerging core asset of utility companies is a customer care center. Believe it or not, network communication and automation plays an important role in providing quality customer service. They are used to improve and automate various processes like billing, product activation, invoicing, claims management, and house moves. Such applications help the utilities offer better customer service at a lower cost, as well as manage the utility's cash flow. Maintaining a precise billing system is a key IT utility requirement that impacts customer service. Utility companies serve a variety of customers with widely different requirements, such as heavy industries that require large amounts of energy, telecom IT companies that require reliable energy, and individual households that require inexpensive energy. It is important for a utility provider to be able to distinguish between customer requirements using a variety of products and prices. Advancements in energy metering provide increased functionality and cost-effective solutions to gathering information throughout a utility grid. Meters are devices that provide data to utility owners and operators that can be used to reduce energy and utility use, reduce energy and utility costs, improve overall building operations, improve equipment operations. Using energy metering devices, facility managers and operators can observe real-time data and analytics regarding where and when energy is being consumed. This information is critical in optimizing building and equipment operations and can help in planning future utility procurements, energy budgets, and tracking approaches. While there are many advanced metering devices available, there is a difference between advanced meters and smart meters. Advanced meters are typically developed with a customer or end-use focus. They measure and record interval data and transmit the data to a remote location. Advanced meters offer a variety of measurements, recording intervals and communications options. For federal compliance, measurements of power, kW, and energy, kWh, are important. Beyond these, the options expand to potentially useful diagnostics within the monitoring of voltages, currents, power factor, power quality, and statistical capabilities. Smart meters are developed largely to meet utility needs and the increasing sophistication of the distribution grid. Smart meters are focused on the big picture. In many cases, these meters satisfy the legislative mandates of interval data and remote communications. However, beyond that, their capabilities focus on utility infrastructure needs and grid interconnect. Smart meters focus on providing utility with time-differentiated energy use. A large driver in smart meter technology is a need to capture and report interval energy use for demand response programs and expected time of use pricing rate structures. Additional utility applications include remote meter reading applications and service connection and disconnection abilities. In this module, we have seen that electric utilities can be divided into three main categories, and each is responsible for serving different types of consumers: residential, commercial, and industrial. New regulations and a need to increase efficiency has necessitated changing the electrical grid system to a smarter system. The energy industry is regulated by standard organizations such as IEEE, IEC, KEMA, and NERC. NERC security directives play an important role due to grid security risks. Automation communication protocols such as Modbus, IEC 61850, IEEE 1613, PTP, and Goose are widely used. To support a robust network architecture, the energy utilities industry has IT requirements such as availability, redundancy, wireless connectivity, and secure remote access. Energy utilities must consider physical topology and environmental conditions and high availability in the selection of equipment and protocols for use in the network.